Thank you for having me here. And I think Peter was mentioning that there is not yet a theory of complex systems, which I fully subscribe to, but we have to work on a theory for complex systems. I think that's our task. And one component of that theory will be to understand the statistics of power laws. Everything you touch in complex systems will have power laws. If you have studied physics, everything in physics was designed, almost everything was designed, that you could describe it with Gaussian functions or exponential functions. Almost everything in physics was dominated by Gaussian statistics. Almost everything in economics is dominated by Gaussian statistics. But basically everything in the real world is not based on Gaussian statistics, as we will see. And it's therefore extremely important to learn about the statistics of power laws. And Locke, in the previous lecture, has already begun to show you one way of getting power laws. What I would like to do now is to show you a handful of ways of how you get power laws. And at the end, I will show you also an idea of hours, how you can get power laws, and that's a work that you can find published here. So power laws are everywhere. It's hard to control them. Compared to Gaussians, doing the mathematics for power laws is a pain. And but it's doable, but it's boring and hard, and you make mistakes, and it's just the way it is. But the computer does not care. That's a good thing. Yeah, and I will now just show you a couple of situations where power laws are coming from. Some of them overlap with what you have just previously seen, just to give you a taste where these things come from. Locke has shown you the city size distribution. So there's very few huge cities, big cities, and many, many, many small cities. And power laws, is there anyone who does not know what a power law is? Could be, if you don't know. It's a function that if you plot it in double logarithmic plot, when x's are logs, is almost is a straight line. Then you have a power law. Yeah? And when you see something like almost a straight line in the tail of it, then we sloppily still call it a power law. This is not a straight line. So, and there's a region where it's certainly not straight. It's shaded here. But there's another region where it's more or less straight. And that's the region we're interested in. Why are power laws important? Because they decay so slowly. If we plot a power law, if we plot an exponential, this is a function that decays somehow. If we plot a power law in contrast, it goes like this. Okay? It does not decay. At a reasonable distance here, this can be a factor of 100,000, 10,000 bigger than this one. That's implicitly why it's so much more easy to deal with exponentials and Gaussians, because they decay after a certain range. You just don't care about them anymore. Whereas with power laws, they decay slowly, and the way they decay is contains a lot of information, which is sometimes critical. Okay, city sizes are distributed like power laws. Rainfall is maybe a self-organized critical phenomenon. So the size, the amount of water that comes down in an individual rainfall, if you make a histogram of many rainfalls, is a power law. The origin could be that it's a self-organized critical thing. Landslides, it's not happening in Singapore, but everywhere else in the world, is that mountains come down. The size of these landslides are power law distributed. The damages in euros due to hurricane damages are power law distributed. So, meaning there is a few hurricanes that are extremely costly and many hurricanes that cost not so much. The credits in the financial system are distributed as power laws. Very few huge loans, very few big credits in the system, very, very many small credits in the system. This is a very nice power law. Forest fires, Locke has shown us. The size of a forest fire every time a forest is burning in different regions in the US, you get one dot. If you plot the frequency of the size distribution of how much area is burned, this is a power law. The moon crater distribution is a power law, very nice power law. Now, what does that reflect? That reflects the energy of meteorites that are floating around in space. Yeah? So why are they power law distributed? I will show you a way of understanding this one. It's certainly not a self-organized critical phenomenon behind the energy distribution of meteors. There's no feedback of meteors. Once they fly, and follow Newton's laws, but there is no self-organized stuff there. If you look at the energy distribution of gamma rays that come from the sun, it's a power law. It's of course, not really a good power law, but more or less. If you look at movie sales, it's a power law. If we look at healthcare costs, it's a power law. If we look at particle physics, if you look at the for those who are physicists, if you look at the cross section of particle events, no. If you look at the energy distribution of particles, then that come out from experiments with accelerators, you find a power law. I will show you again a new mechanism that might explain that. It's also not a self-organized critical phenomenon that leads to this. Words in a book, Locke has shown you, is the famous Zipf law. If you are not sleeping well because you have jet lag or something, and if you have a very bad book to read, then you can do a very boring thing. You can count the number of words in your book, and then you can order the words according to the frequency, how they appear. It must be really bad literature, but this exists. And then if you ordered your word, the words in order of appearance, then you see that the most frequent word appears n times, say 1,000 times, The second frequent word appears half of that time, 500 times. The third frequent word appears a third of that. 1,000 divided by 3 is 333, etc. The 1,000th most important word appears one time. Yeah? So this is Zipf's law, a power law with an exponent of -1. There is at least 5 mechanisms that explain this power law. One is preferential attachment. One is a mechanism that Locke told you. It's monkeys writing on a typewriter. And I'll show you a third one. Mandelbrot, who was also mentioned in the connection of fractals, he has an explanation for this law, which is very unrealistic. Yeah, I'll show you an alternative. Citations of scientific articles are distributed like power laws. Website hits are distributed as power laws. So how often are people clicking on different web pages? They're clicking very few times. Very few pages are clicked on millions of times. Most web pages are clicked on very few times. I'll show you a mechanism that might explain the reason why this is happening. It's also not a self-organized critical process. Book sales, telephone calls, earthquake magnitudes are all power laws. Earthquake magnitudes is the Richter law, Locke has told you. That's maybe the power law that you learn earliest in your life. The number of seismic events is a power law. Social events like wars are riddled with power laws. War intensity, killings in wars, sizes of wars, these are all power laws. Wealth distributions in populations are power laws. People are debating if this is really true, especially for people who are not so wealthy, like all of us. We would be on that end. In that region, it's certainly not a power law, but in the tails, again, of the wealth distribution in almost all countries, it's a power law. The way how family names are distributed in the United States is a power law. And we have not mentioned all of these things yet. So whenever you take a network, you will find, literally thousands of examples of where you find power laws or approximate power laws in networks. Wherever you look in biology, in physiology, you will find power laws. People from the Santa Fe Institute could explain literally dozens, maybe hundreds of these power laws within one single framework. So, very beautiful work by Jeffrey West, who gave a lecture at this course last year. Dynamics in cities. So how do people, what's the walking speed of people in a city? This is a power law. If you plot the walking speed against city size, this is a power law. If you plot the earnings or the income of people in a city as a function of city size, this is a power law. And again, dozens of more of these power laws. Fragmentation processes. If you have a spaghetti, if you break it, and if you keep breaking it, if you look at the end of the distribution of fragments, in many situations, if you follow certain breaking rules, you will find power laws. many variations of random walks are power laws. In physics, crackling noise, what is crackling noise? You can think of taking a sheet of paper and you could crush it, or not crush it. You could just, I don't know the English word. You could crumble it. You could crumble it. And if you put a microphone next to it, and if you analyze the sound it makes, it's a power law. And there's, of course, hundreds of phenomena in the real world that follow this. The way blackouts are happening in the industrialized world is power laws. The fossil record, so even in ancient times, is full of power laws. How often you see what kind of bird in bird watching things is power laws. Terrorist attacks are power laws, etc., 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 etc. Show me something that's not a power law. So it's, and then you will show me some things in physics, maybe. So where do they come from? There is maybe 4 classic ways of understanding where power laws come from. And let's just go through them that you know that. It's not that there is 100 ways of generating power laws. It's a handful of ways. The first time where people understood where power laws come from is from statistical mechanics. Locke has told us about this a little bit. Second way was the theme of Locke's talk. The power laws come from systems that behave self-organized critical. If we have multiplicative processes, we get power laws. And if we have preferential processes, we get power laws. These are the 4 classics of getting power laws. Let's discuss them a little bit. In statistical physics, power laws arise at phase transition, at a critical point. So if you think of a magnet and you're heating this magnet, then this will not be a magnet. But if you're cooling that magnet, there will be a critical temperature at which magnetization appears. It's the Curie point. You have all, I don't know, maybe you've not all heard of this. Here's temperature, here's the magnetization. If temperature is very high, what are atoms doing? They are flipping around like mad. They're not organizing, they're not aligning. And there's a critical temperature, the Curie point, at which magnetization starts appearing. This is a critical point. And at this point, we see that if you compute a correlation function between the spins of these atoms, that at this point you get power laws in these distribution functions. Here, the correlation functions are exponentially decaying. At this point, they become power laws. Okay? This is where, in statistical mechanics, people found out and understood everything about power laws. If you have one material, one magnet, then there is very often more than one physical phenomenon that you can describe. It's not only magnetization, it's also the susceptibility or other things. And to many of these different phenomena, there exists a different power law exponent that characterizes the material. So there's a handful of exponents that characterize a phase transition in physics. And this collection of exponents is called the critical exponents. With these critical exponents, you can characterize what's happened. You can classify all materials, basically. And what is the fantastic thing about this is that also every model that you can make, the Ising model, which was mentioned, for example, has also a number of exponents. And if the exponents of the model match the exponents of your material, you know that your model is the exact model for your material. So this is one of the few cases where you know that your model, even though it's unrealistic, is predicting the system exactly. This is what people call universality, and is one of the triumphs of physics in the 20th century, I would say. We have heard everything about self-organized criticality. I will not mention much. Let me just mention a couple of examples. So also here I should mention some examples. It's magnetic materials. Basically, in physics, it's kind of boring set of examples. The set of examples for self-organized criticality gets much more interesting. So earthquakes, all sorts of collapse processes, all sorts of disasters, lots of dynamics in the economy, in the financial systems that are going on is related to self-organized critical systems. Okay, intermission. Third classic mechanism to get power laws is multiplicative processes. What is a multiplicative process? We all know that if you have random numbers, which are not too crazy, which are not from a too crazy source, meaning that these random numbers have a finite variance. But if you generate random numbers, and if you add them up, the sum of these random numbers will always be Gaussian distributed. This is the central limit theorem. Is anyone here who has not heard about the central limit theorem? Oh, you all did. Okay. What happens if you multiply random numbers? Exactly the same random numbers that we had before. Let's multiply them. From which distribution is the product from? Oh? Huh? Say it again. What is the question? So, the first thing is the first thing is that you tell me you know that when you are adding random numbers, the sum of this will be from a Gaussian distribution. The question now is, if I'm not adding these numbers but multiplying them, from which distribution is the product from? Okay. You could find out easily. If you're multiplying two numbers, and if I take the logarithm of it, this is the same as adding two times the logarithm. No? If A and B is random numbers, the logarithm of A and B is random numbers. Does it change the variance? Yes, it does, but it keeps finite. If I'm adding random numbers, what do I get? A Gaussian. Okay, so I know that the logarithm of multiplying random numbers gives a Gaussian. So if I take this log away by putting in an exponent, an exponential in front, then I get the distribution for the product of random numbers. Okay? And the distribution is called log normal. Normal because the Gaussian is there, and the log because there's a log here. Okay? The log normal distribution is very, very close to a power law. It's of course not the same, but for many situations, when you have data, for example, you cannot really say, is this a power law or is this a log normal distribution? And there is a situation that if you put some constraints on how you draw these random numbers, if you put some constraints on it, the log normal will become the distribution function will not become a log normal, but an exact power law. So multiplicative processes with certain constraints will lead to exact power laws. That's why these multiplicative processes are a classic way of generating power laws. So what could these constraints be? Could be that any random number that you are sampling should be larger than a given minimum, for example. That is enough already. Or that the sum of all random numbers is above or below a certain threshold. Constraints of this type are enough to produce exact power laws from multiplicative processes. Locke has also mentioned this a little bit. Peter has mentioned it. Power laws arise through preferential processes. Preferential processes are processes where the frequency or the strength of a process depends on the previous strength or frequency of how often a similar thing has happened in the past. Simplest example is how scale-free networks grow. Peter has shown us a movie this morning where you're adding one node to a network after another. And what the node is doing, it attaches somewhere to the network. And how does it do that? The probability that it attaches to a node is proportional to the number of links that node already has. We call it preferential attachment. If you keep doing this, you will generate a scale-free network. What is a scale-free network? It's a network with a power law. And what is the power law? The degree distribution is a power law. Is there anyone who does not know what a degree distribution is? Yeah. Good. If you have a network and you grab in blindly into that network and you pull out one of the nodes, then you can ask how many links does that node have? The probability of finding X or K links in any given node is called the degree distribution. Probability of finding a node with a certain degree is the degree distribution. And this degree distribution is a power law. And if it's a power law, you call the whole network a scale-free network. Scale-free and power law is used in the same way. It's the same thing. Is that clear to everyone why power laws are scale-free? Seems to be.
In the previous slide, you mentioned that language formation is a preferential process. I was wondering if you could elaborate on it.
Yes, I can. Language formation is not a preferential process. I'm almost sure it's not. But a very famous person, Herbert Simon, tried to understand Zipf's law by a preferential process, where he assumes that I'm forming texts in the way that the probability of using a word, the next word in a sentence, for example, is proportional to how often I have used that word in the text before. If I'm doing that, I get Zipf's law. For exactly the same reason why we get scale-free networks. If the next words, if the probability of using a certain word as the next word in a sequence is proportional to how often have I used that word in the sequence, I get a power law of word frequencies. That's not how we are producing language. In fact, it's exactly what your English teacher told you not to do. Don't repeat words too often. Yeah, and especially if you use words many times, avoid them. Don't. Yeah. So that's the reason why I put it here. There is models that use preferential processes to understand language formation. That does not mean that that's a good way of understanding it. So there's a couple of other mechanisms where we don't go into it. Levy-stable processes lead to power laws under certain conditions. You look that up on Wikipedia. That's classic statistics. Also, classical statistics is extreme value statistics or record statistics. Yes, in statistical mechanics, it was popular for some time to talk about return times. How long, if I'm somewhere in phase space, how long does it take if I'm having a process, how long does it take to come back to this first point? In many systems, return time distributions are power laws. And we did not, we don't have any tool now with these mechanisms that I've shown you. We don't have anything to understand power laws from dynamical processes that are history dependent. Many processes in the world depend on the history, meaning that the next steps that you take depend on what you have done before. Yeah. A little bit, or the only mechanism that we have discussed that is doing that is preferential attachment. Where the whole history matters what's your options for the future. But this is just a very particular point, a very particular way of seeing things, this preferential attachment. I'll show you something much, much broader in scope. So, a history or path-dependent process means that the future depends on the history of all the past events. Yeah. Very often you have processes where, as they unfold, they get more and more constrained. Yeah? For example, the more education you get, the more constrained is your career path. The more you learn, the less you will do completely random things. Yeah? So there's many processes in this world where the sample space is reducing as processes unfold. We'll talk about this. So we'll talk about sample space reducing processes. Maybe the simplest way of thinking of a sample space reducing process is that if you have a set of dice, you have n dice, and die number 1 has 1 face. Every time you throw it, it gives 1. It's a stupid die. Die number 2 has 2 faces. It's a coin, gives 1 or 2. Then you can have a die with 3 faces. I don't know how to produce one, but you could think there is one. And die number n has n faces. And the sample space reducing process is now a process of this kind, that you take the biggest die with n faces, you throw it. Whatever number it gives, let's say it's 17, in the next time step, you take dice number 17 and throw this one. Now you get a number between 1 and 17. Whatever you find, let's say 7, you take die number 7 and keep doing that until you hit 1. Every time you're throwing the dice, you're reducing the number of possible numbers you can get. Okay? This is maybe the simplest way of thinking of it. I think that sentence formation is exactly of this kind. When we are producing a sentence, we have to pick a first word. Where do we take it from? We take it from the English vocabulary. So here's the English vocabulary. I can pick any word and start a sentence. This is taking the big dice with n faces. I have n different words to choose from. My lexicon has n words. I just pick one word to start with, starting my sentence with the wolf. As soon as I pick this word, I have lots of constraints. I cannot pick any other word. Why do I have constraints? Because there's grammar and there is context. So if I pick a noun, then I'm now forced to use a verb. I cannot, and who is telling me this? Grammar. If I'm not doing that, it's bad English. So as soon as I pick something, I'm reducing the total space of possibilities to a subset of it. And as soon as I pick a verb, I am again constraining myself to another subset of words. And this keeps going until I come to the point. Yeah. Okay? So usage of language is a sample space reducing process. Here's another way of seeing a sample space reducing process. It's basically a staircase which is numbered from 1 to 10, and you have a ball which is allowed to hop random distances, but only downward. Okay? So it can go down, but must not jump upward. If we have a staircase that's flat, meaning that the ball can go left and right, we just have an ordinary random walk. At every point in time we jump left or right. Then our distribution function of how often we visit state 1 up to 10 is a flat distribution, a uniform distribution. If we are looking at this process, the distribution function will look like something like this. We visit state number 1 as many times as we start the process. We visit state number 2 less than this, 3 even less than that, etc. And it turns out to be that the probability of visiting state number I is equal to 1 divided by I. This is exactly Zipf's law. It's the simplest power law distribution that you can get. Yeah. So P of I is I to the power -1. That's what people call Zipf's law. Alpha, the exponent, being -1. So you have to prove that this is the result for this idiotically simple process. We're not going to prove it, but this is all of what the proof is. It's 10 lines, basically. Yeah. So this gives us a way of explaining Zipf's law as a sample space reducing process. Most processes, or most so P of x or I is proportional to x to negative alpha. Most exponents are not -1. In many processes, you find that alpha is close to -1, but most of the time it's not. And so how can we make our theory a little bit more general? We can say that in principle we have to jump down the staircase here, but with a certain probability we can also jump upward again. That is nothing else but saying I'm combining the pure staircase process where I can only jump down. I combine this process with this process. I'm adding, in a sense, adding these two processes, and let's see what's happening then. So we denote the staircase process where we only can go downward by phi, and the process where we can jump left and right by phi sub r, random walk. Okay? And if we give different weights to both of these processes, lambda to the staircase process, 1 negative lambda to the random process, we can, it's another proof of 10 to 15 lines, we can prove that the probability distribution of finding state number I is I to the negative power of lambda. So now we have already a much stronger theory. Now we can already explain every exponent between 0 and 1. Okay? Maybe half of all the processes in the world have that. Yeah, that's the proof for it. It's not longer than that. And if you don't trust it, you can program it in a little MATLAB code. Maybe you can do that as an exercise, I don't know. Yeah, you can simulate it. You believe me that this is the case. This law that I've shown you, this way of producing a power law, is extremely robust. What do I mean by that? So if we have again a random process where we put different probabilities, prior probabilities to visiting the states. So visiting state 6 has a much higher probability than visiting state number 3, for example. When we are sampling that process, we're letting the ball jump left and right, we will get a probability distribution that looks something like this. State number 6 will be visited many more times than state number 3. Okay, why? Because the prior probabilities, which are depicted here as the width of these intervals here, is just that. If we have a staircase process where we also have the same prior probabilities here, we could imagine that we would also get something like this, but we don't. We get, again, Zipf's law. We get exactly this thing again with alpha being -1. This is completely crazy if you think of it. Or not crazy, it's unexpected. And no matter how you change these prior probabilities, you will always get this power law. This is a sign of extreme robustness, and this might explain why you observe power laws so often. Because no matter what your how you are designing your system in detail. In detail means fixing the prior probabilities of how often states should be visited. If you don't have this staircase dynamics on top of it, no matter how you design your system in detail, you always get this law. Okay, we can even take out huge parts of our staircases, huge parts of our sample space, and we still get this. Good. Let's try to find applications for this. And what I would like to do in the next couple of minutes is to, how much more time do I have? 5 minutes? Okay. Or no, that's according to schedule. This I know myself. But I started much later. Okay. You can view this kind of process as a diffusion process on a network. A network that has 10 nodes, and you can jump from node to node, but every node has a number, but you can only jump from one node to the other if the node number where you're jumping to is less than the number you're starting from. Okay, so it's a directed graph, and since you're not allowed to jump upward, there's also no cycles in this graph. So it's a directed acyclic graph. This process is a diffusion process on a directed acyclical graph. Meaning that every time you have a diffusion process on such a network, you are going to have Zipf's law present. And this is a big statement. Zipf's law in what? In how often you're visiting nodes. Yeah. So the node that you're visiting most is visited n times. The node you're visiting second most frequently is is visited n half times. The third most visited node is visited n third times, etc. So this magic Zipf's law appears whenever you have diffusion on a directed acyclical graph. Okay, so we need a graph, we need numbers, we have to give names to the nodes so that we can direct it, otherwise we cannot direct it. And then we just diffuse. Wherever we start, we can only go along the line of where the arrows are pointing. And if we are counting how often we visit which node, and then order it, make a rank frequency distribution out of it, we will get this curve. Okay. Now, an acyclic directed graph, this process is the same as a fully connected acyclic directed graph. What if it's less than fully connected? Typically, fully connected networks are pretty boring. So what if they are not fully connected? If you're taking out links, then you still get Zipf's law. Why? Because we have this extreme robustness sitting there. Yeah? We can cut out things I've shown you before on a slide, and still this is present. So here's an example. Here's the link density. This is a fully connected graph here. Here's not connected at all and everything in between. This is the exponent alpha here, which is 1, 1, 1, 1, 1 for thousands of simulations on small networks, it's always 1, and only if it gets very, very sparse, the exponent comes down. Does the topology of the network matter? No, it does not matter. If you have a scale-free graph or an exponential graph or any realistic network taken from the literature, and if you have a diffusion process on it, it will always give you this distribution in the visiting times of nodes. So, why? Because prior probabilities are irrelevant for the system. If we put weights on the links, does it change? No, it does not change. We get exactly the same -1 exponents. We get this graph. Things start happening if we are allowed to introduce cycles. Now we had it acyclic, but if we introduce cycles, if we allow things to go in loops, depending on the density of cycles, we now see the slope change. Okay, so now it's not only -1, it's anything between 0 and 1. So by measuring the visiting times of nodes in a network, I can deduce the density of cycles in it, which makes things much, much simpler than counting triangles. So Zipf's law is an immense attractor. No matter what the network topology is, no matter what the link weights are, you always get Zipf's law, exactly Zipf's law, meaning alpha being 1. And if you have cycles, the exponent becomes less than 1. But it remains an exact power law. Can we get exponents larger than 1? Meaning that we go from 0 to infinity? Do we have that spectrum present? Yes. What do you have to do? You have to, if you start with a ball here, as soon as you start jumping, you double it. Yeah, you're fragmenting it. So one ball lands here. Whenever this one starts going down, it doubles. Assume, if it doubles, this alpha becomes a 2. If it triples, alpha will become 3. If every time the thing splits into 17 particles, the exponent will be 17. Okay? So the splitting rate becomes your exponent here. And through this, you have a mechanism with which you can explain any power law. So whenever you have a sample space reducing process at hand, and you know about the details of it, meaning is it coming from a diffusion on a network, or is it the result of a fragmentation process? These are fragmentation processes. And here we come back to the moon crater distribution, which is about, this is about somewhere between 3 and 4. You can cover it all with this little concept here of this staircase process. So now I'm out of time, I guess, which is not really true, but let me just finish by mentioning that whenever you're searching for something, every time search is involved in anything, and if your search is a good search, you have a sample space reducing process. What is a good search? Good search is that you don't have to look, if you lose your keys, that you don't have to look at every square centimeter of this room to check where this thing is. But if a good search is, if I open the door and then I close it and say, it's not in here. Every step I make excludes many possibilities. Then I have a good search. So whenever you're searching for something, you have a sample space reducing process, and you should observe power laws. Do we observe these power laws? Yes, we do. The click rates for example, on web pages. Very often, when you click on a page, this is the result of a search process through whatever engine, can be Google or can be a suggestion from a friend, try to look for this. Then you're searching for something, and sure enough, you will find power laws there, exactly of this kind. In some companies, they're looking how the employees are actively searching for things. For example, when you're writing computer code, how do I find a piece of code that I need? How do I search for it? Companies keep track of it. And for different companies, when you analyze the clicking behavior or searching behavior of their employees, you find always the same power law, always Zipf's law. Yeah? Meaning that the guys are doing good searches. Okay, so maybe to summarize, whenever we have diffusion processes on cyclic directed graphs, we understand the power laws that come from that. Whenever we have fragmentation processes and observe power laws, we have an explanation for that. Whenever we have search processes, we have an explanation for that. Also, we think sequences of human behavior. So there's recent works on it, shows fantastic power laws, is sample space reducing. So I think that's a theory for it. Games, like the game of Go, is for large parts of the game, it's sample space reducing. Everything you do constrains you, and you find fantastic power laws in the game of Go, which we think we can explain. We're looking for a PhD student to really show that. Yeah, okay. And what did I show you? Many processes in this world are history dependent. This sample space reducing processes are an example for history dependent processes, simple history dependent processes. I showed you that power exponents depend on the noise level in the system. I did not tell you what I mean by noise. By noise, I mean how strong is the component of the pure random walk. Remember when we combined these two, the thing where we go down and the other one where we are not going down. The one where we are not going down, this is a random walk. This is, I call noise. Going left and right with the same probability. And so the strength of the noise determines the power law. So we can use the measurement of exponent of inferring what's the intrinsic noise levels of processes. I've shown you that this mechanism of sample space reducing statistics is extremely robust, no matter what the topology of a network is, what the links are, etc. It simply doesn't matter. You always get this distribution. Good. And I've shown you that every search process and every fragmentation process can be, the statistics of these processes can be explained by this. Thank you.